Hi, we are Billy, Chinese Raps Ryan from Group 6, and our project is pneumonia pre-classification by chest X-ray using convolutional neural networks. I'm Chenny, and now I will talk about why we want to do this and the basic information of our dataset. In 2020, the most influential thing is the outbreak of COVID-19. However, the capacity of process testing approach of it, like PCR test and CT scan, are limited or even unavailable in some regions. Since COVID-19 can cause viral pneumonia and viral pneumonia has a unique feature on chest X-ray, X-ray might be a tool to help doctors screen suspected patients. So our project is to build a CNN model to assist radiologists in screening patients by chest X-ray, just for assistance, not do diagnosis. Then let's talk about datasets. Our dataset was downloaded from Cargo, which includes 5,1863 training chest X-ray images and 624 testing images in 3 categories. Here is 3 samples from 3 classes. The normal chest X-ray depicts clear lungs without any areas of abnormal opacification. Bacterial pneumonia typically exhibits a focal lobar consolidation, whereas viral pneumonia manifests with a more diffuse interstitial pattern in both lungs. Besides, we found the training set has an unbalanced class distribution, so we set class weight for training according to the proportion of each class to avoid bias caused by it.
My name is Ryan Wang. I will talk about our model. First, we perform data augmentation in order to prevent overfitting. We use 2 different network structures. The first one is simple CNN. We construct 4 convolutional layers and 3 dense layers. Our second model is Xception Network. We maintain the 36 convolutional layers in the original paper. In the end, we add 3 dense layers in order to transfer the network into solving our classification problem. Our intuitive idea of using Xception model comes from 2 great parts of Xception Network. The first is that it uses 1-by-1 convolutional to reduce the channel size. The second is that it contains structure called an inception block so that it can extract multiple features in one layer. As for the training process, both models use the loss function of cross entropy and the optimizer of item. We build a customized early stopping function that selects the average of categorical accuracy, recall rate of pneumonia, recall rate of viral pneumonia, and recall rate of normal people. We set patient to 5 and epoch to 30 after tuning parameters.
This is Billy. I'm going to talk about visualization and evaluation. Here's the confusion matrix showing our model works well. We have over 85% accuracy and recall rates, where the total recall rate is 97.2%. To further validate our model, we visualize intermediate layers. This image is from viral pneumonia class. From the picture, we could see some nodular opacities, which is a sign of viral pneumonia, and we hope our model tunes it. At the most beginning, our model ejects the edges of the ribs and organs and also the opacities, which is of importance to find out pneumonia and classify it. When the model goes deeper and deeper, the feature maps become less interpretable and there remain only several pixels. We also have saliency maps and grid caps. Unfortunately, the saliency maps are meaningless. This may be because the model is attempting to find some small regular patterns like interstitial shadows, which is good since it is what we want to learn. But it may just because the fact that the saliency tools do not support the models of Xception families, including Xception well according to its documentations. But luckily, we still have grid caps. In most correct samples, the model focuses on the correct area where some shadows appear, suggesting the pneumonia. However, there are some exceptions even the predictions are correct. For example, in the PowerPoint, when the heart border and the diaphragm disappear, the feature map actually look at the angle of the right lung. In some wrong predictions, the model becomes ever ridiculous that it looks at the shoulders instead of the lungs.
I'm Rabbit. I'm going to introduce the improvement strategy. The results of our model are okay, but they still have some problems. Our datasets are from children between the ages of 1 and 5, but the bodies of children in these ages are growing rapidly. The gap between samples can be large, so our next priority is to find a more appreciated training set, especially for adult chest radiographs. We found the largest chest radiograph dataset published by NIH Clinical Center. However, it only had a label of pneumonia and doesn't distinguish between viral and bacterial. So we also need a real radiologist to help us distinguish these samples. Additionally, just as the purpose of this dataset is to create a high-precision computer system, we want to create a new model to classify all diseases in this dataset. In fact, an article was published on the topic in CVPR 2017, which also provides labels of dataset. They have tried AlexNet, GoogleNet, VGG16, and ResNet 15 on this dataset, in which the better one is ResNet 50, but its accuracy is far from practical. So our future task is to use their work as a baseline to continue to try other models or modify some existing models to achieve high accuracy. These are our references. Thanks, and we will take any questions.